we're going to use a method called separation of variables. And it's exactly what it sounds like. It is separating the variables, x's and y's, okay? You technically have solved differential equations before by finding antiderivatives. Every time you find an antiderivative, you're solving a very basic differential equation. Y prime equals whatever that derivative was, right? You're finding the function that satisfies that equation. But these kinds of equations with x's and y's in it are where it gets tricky, right? Because we need to find the equation for y such that the derivative satisfies this, right? Unless you want to just start guessing random functions and plugging it in and seeing if it works. It'd be better if we could solve them in a method, right? Instead of just guessing a ton of functions. So one of the methods is called separation of variables, and it goes as so. So first of all, y prime means the same thing as dy dx, right? So you always want to write y prime as dy dx. And then the goal is to separate all the x's on one side and the y's on one side. And when I mean the x's and y's, I mean dx needs to be with all the x's and dy needs to be with all the dy's. So usually you're going to be moving your y's to the left if dy is on the top over here. If your dy was over here on the top, then you would move it over here, but usually it ends up being over here. So we're going to move our y's over here with the dy, and then we'll move our dx over here with the x's. How would I move this y to that side? Multiply. And then how would I move the dx over to that side? Multiply by it as well, right? It looks a little weird to do that, to separate it, but we can't, it's being divided, right? So we're just going to move it over to that side. So this is the separation of variable part, right? This is always the first step. So now my y's are over here and my x's are over here. Once you have separated your variables, you're going to integrate both sides, because now that you have one variable, you're just going to find an antiderivative, right? So what's the antiderivative of 2x? X squared. What's the antiderivative of y? Yeah, just add 1 to the power. So y squared divided by 2, right? Use your reverse power rule. And then usually what do we put on on the end of our, that's a little scary. On the end of our antiderivatives? A plus c. So you could put 1 on each side, but that's kind of silly because then you could just move 1 over to the other side and merge them together to be constant. So we're always going to put it on the x side. And at this point now, we really have found a solution to the differential equation. But usually when we look at solutions, they're in the form y equals. So usually what we'll want to do is then go ahead and solve for y. So if we multiply by 2, that 2 will multiply by the c, and I'm going to write c2 here because that's a different constant than this. A lot of times you're going to see people just leave it as c because it's just a constant, right? Doesn't really matter. As long as you can understand that it's a different constant than the first c that you had because you multiplied it by 2, then it doesn't really matter whether you write c or c2. But just to kind of help y'all get convinced of the differences between the c's, I'm going to leave it as a c2, okay? And then we'll take the square root of both sides, and we'll have y is equal to plus or minus the square root of 2x squared plus c2. So there are 2 different types of solutions to this differential equation, the positive version and the negative version, okay? And then this is a general solution because this is infinitely many solutions because c can be anything we want, right? It could be 1, it could be 2, it could be 3, it could be 5, it could be 10, it could be 100, right? So this is a general solution because this is infinitely many solutions here because c can take on any value, right? Eventually we'll find some particular solutions and we'll figure out what c needs to be. Yeah.
Is that 2 next to the c, or is it a subscript?
It's a subscript.
Okay.
Yeah. I'm just calling it a different constant since I multiplied this one by c. So it's still a constant. I'm just calling it c2 instead of c. So that's how separation of variable works. Okay. Sometimes the hardest part is the actual separating the variables, the very first step. So let's practice a little bit of that. Oh, actually, also important note. Some people forget to add the c and then they go back in and just add it on at the end. That's not going to work, okay? You have to add the c as soon as you find the antiderivative because this c being under the radical is very different than a c being outside the radical, Okay, they're not the same thing. Okay, so you have to make sure you add it at the appropriate time. Okay, so let's just separate the variables on these ones. We'll do the first one together. So here, this one's a little bit interesting. What do you think? My dy is on the top over here, so let's keep our y's on this side and move the x's to the other side. So what do you think I should do first? Subtract x squared. So we'll have 3y dy dx is equal to negative x squared. And now the only other thing I need to move over to this side is what? What else needs to be over there? Not yet. Not until we find the antiderivative. The dx, right? We want all the x's on this side, including the dx. So now multiply the dx over, and you'll have 3y dy is equal to negative x squared dx. So that's the separation of variables. We're not going to continue this one. We're just going to separate the variables. So now I want you to try it for the next two. Try separating those variables. Remember to write y prime is dy dx. Go ahead and compare what you did for those two with your table. Compare how you separated your variables, what you ended up getting. Takes a minute to get used to, so don't fret. All right, first one, what did y'all do first? I think everyone probably did the same thing first. Divide the sign over to the other side, right? We want it over there with that x, right? So when you divide by sign, you have cosine over sine. What's cosine over sine? The same thing as cotangent. Don't forget to write your y prime is dy dx, because then the very last thing you'll want to do is move that dx over there. So dy will be equal to cotangent of x dx. This one's a little bit more complicated, but if you kind of just think about how to get rid of stuff, you can kind of tend to do a lot of it in your head. So first I just rewrote y prime as dy dx. I'm going to keep my dy's over here because dy is in the top, and I'll move my x's over there. So this gets to stay, right? Either the y plus 1 can stay. What do I need to move? I need to move the x and the dx. How am I going to move the x? Divide, right? And then how will I move the dx? Multiply. So I should have 1 over e to the y plus 1 dy, or you can have the dy in the top. If you just left it in the top, that's the same thing. And then I'll have 2 over x times dx. Because I just divided by x and multiplied by dx. Okay? Any questions about the separation? All right, let's actually try to solve a differential equation together again. So first one down here, this next one, we're going to solve it, but I want you to do the separation of variables. So start by separating the variables. Hopefully you move the cosine of y over by multiplying, and then dx over by multiplying. Once we separate variables, anyone remember what I told you to do next? Yeah, integrate both sides. So go ahead and find those antiderivatives. What's the antiderivative of cosine? Sine. What's the antiderivative of 4x cubed? X to the fourth. And where do we put the plus c? On the x side. And then the very last step is usually that you want to solve for y, as long as that's possible, right? So if I'm going to solve for y here, how am I going to get rid of that sine? Inverse sine. Yep, arc sine. So that'll be y is equal to inverse sine of x to the fourth plus c. And again, this is a general solution because there's a c there. So now we'll start to look at particular solutions. Because this is infinitely many solutions, right? You can pick infinitely many values of c, and that will still be a solution to the differential equation. Any questions? Okie dokie. So now let's do a particular solution. When you have a particular solution, they're going to give you x and y values, and then you can actually figure out what c is, right? Because you're going to select, just like when we were doing the slope fields yesterday, if you go through a particular point, you now have indicated one solution you're talking about, right? Not all of them, okay? So we're still going to solve it by finding the general solution first. So separate your variables. So it might be a little bit tricky. Try to separate your variables. So I definitely want the x squared plus 4 over here. I cannot go in and subtract x squared, right? Because that's all being multiplied by that. So you definitely cannot subtract x squared out. That's all being multiplied by dy dx. But I can move all of this over to that side, and then I can move the y over to this side. So if I move the y over to this side, I'll be dividing by y. So we'll have 1 over y dy. And then if I move this over to that side, I'll be dividing by x squared plus 4. So we'll have x over x squared plus 4. And then if I move the dx over, I'll be multiplying. So this is what your separation of variables should look like. And then we integrate both sides. What's the antiderivative of 1 over y? ln of y. And what are we going to have to do for this one? Ooh, close. It's almost arctangent, but the x in the top is not going to make it not arctangent. It would have to be a 1. Yeah, it's just going to be a u sub. So go ahead and do that. U sub u equals x squared plus 4. So if u is x squared plus 4, du will be equal to 2x dx, so you'll have to divide by that 2. So you'll end up with 1/2 integral of du over u. So this will be 1/2 natural log of x squared plus 4 plus c. And the interesting thing about differential equations is there are a lot of ways to solve them, okay? So I provide you solutions a lot of times with differential equations because I think it's helpful to see them and see how it might be done. But just because you do it differently doesn't mean that that's wrong, right? And you might find someone else that did it completely different than that. And you might watch another video of a professor that did it completely different than that. And that's okay. If you're finding a particular solution, you're still going to get the same answer. At least you should if you're doing it correctly, okay? So one way to continue from here is to solve for y, just like we did on the last one, and then find c, okay? Some people will start by finding c first, and then they'll solve for y, okay? So those are kind of the two main strategies, solve for y first, then find c, or find c and solve for y. Honestly, I do it both ways. Sometimes it's easier to find c first, and I'll do that, and then I'll solve for y. Other times I feel like I know how to solve for y, so I'll do that first, and then I'll find c, okay? So you can do it either way. Let's talk about how you would find c first, and then we're going to actually do it the other way. We're going to solve for y first, and then find c. What do I mean by find c? What would I do if I wanted to find this c value first? How would I solve for c? Like, what can I figure out? Like, is it going to be, is it going to have x's in it? Or should it be a particular number? It should be a particular number. How am I going to figure out what particular number that is? We're going to plug in the x's and the y values, right? This is why this matters now. That we're finding a particular solution, they have to give us an initial condition. So you'd plug in -3 for x, you'd plug in 2 for y, and then you'd solve for c, okay, if you found c first. Then you would plug it in, and then go back and solve for y. We're going to do it the opposite way this time. And I'll show you a few different ways in different problems. So for this one, we're going to solve for y first. If I want to get this y by itself, how do I get rid of that natural logarithm? Yeah, raise both sides to the power of e. But when I do that, I also see this natural log being pretty close to that c, so it'd be nice if those could cancel out, but this 1/2 is in the way. So I'm going to move that 1/2 out of the way before I continue. What can I do with that 1/2 in properties of logarithms? Yeah, move it up in the exponent, right? Because it's a number in front. So first, I'll put that in the exponent. Then I'll raise both sides to the power of e. These guys will cancel, and this will technically become the absolute value of y. We'll kind of be able to ignore that here in a minute. This side, though, we have to be a little careful because this will be e to the ln of x squared plus 4 to the 1/2. And then I'm going to write this as times e to the c. This is an important step. Is that allowed, what I just did? Is that the same as this right here? Question, what do you do when you have x squared times x to the 3rd? You add the exponents, right? Isn't that x to the 5th? Are these the same base? So if you add the exponents, you get this, right? So I'm just undoing the adding of the exponents, right? So I'm separating that into e to that times e to the c. And I did that because now this is a new constant, right? It's e to some constant. So we'll have the absolute value of y. This will cancel out. And you'll have just x squared plus 4 to the 1/2. And then this e to the c is being multiplied by that, right? And so it's just a whole nother constant. We'll call it c2. So just the e to the ln canceled, this all came down, and then the e to the c became a brand new constant. I did get rid of the absolute value right here because x squared plus 4 will never be negative, right? So I don't need to worry about that. So I just turned it in parentheses. And then I'm also going to drop the absolute value around the y, okay? Why can I do that? Well, if I was being precise, I would say, well, this could be, y could be, if it's the absolute value of y, then that means that y could be plus or minus either one of these. They could be either one. But most of the time, you'll just see people dropping that plus or minus because it's going to get sucked into that constant anyway. And so you'll be able to figure, you'll already solve that and you'll figure out which one it is when you find that constant. So you don't really have to worry about it. So that is our general solution. So this is our general solution. There's a few things I'm writing down here that I won't usually write down just to explain what we're doing. So this is the general solution. And now that we have solved for y, we can plug in our x and y values and find c to find our particular solution. So x is negative 2, y is 3. Oh, other way around, sorry. Y is, I'll be looking at my paper. Y is 2 and x is negative 3. So it'll be 9 plus 4 to the 1/2. So this is 2 is equal to C2 squared of 13. So C2 is the square root of 13 over 2. No, other way around. 2 divided by the square root of 13. So then if we take our general solution here, and if we plug in our C2, we now have a particular solution. Some people may have solved this problem by finding C first, and then they would have solved for Y. This time I think it was a little bit easier to find C first, or solve for Y and then find C, but it doesn't really matter which way you do it. Every now and then you might get a problem that's really, really hard one way or the other. Any questions so far about particular solutions? So when you're finding that particular solution, you're just figuring out what C is. Okay, let's do another one. All right, so we're going to find the particular solution. So we're going to figure out what C is. First, we have to start from scratch, separate our variables. This time, the x's and the y's are written kind of interestingly enough. So what do you think we need to do first? These two terms are being added together. Probably need to subtract one of them to the other side, right? You can do whichever one you want, but we've been keeping y on the left. So let's keep y on the left. We'll move the x's over. So we'll keep e to the negative x squared, y squared minus 1 dy over here. We'll subtract x, y dx. Now finish your separation. So move all your y's over here and all your x's over here. All right, so you should have y squared minus 1 over y dy is equal to negative x. And then we'll divide by e to the negative x squared, but since it's negative, I can make it positive and just bring it up to the top, right? So it'll be e to the x squared dx. So I divided by it, but it was negative, so then I just brought it up to the top. And then this will simplify even more too, because this will just be y minus 1 over y dy is equal to negative x e to the x squared dx. And then we'll go ahead and integrate both sides. So go ahead and try that integration. Don't use integration by parts. It is not necessary. So the antiderivative of y will be y squared over 2. 1 over y will be minus ln of y. And what should we use on this guy? U sub. Because if u is x squared, du is 2x, right? And there's an x out there. So that's why you don't want to use integration by parts. So if u is x squared, du will be 2x dx. So you just need to divide that 1/2 over. So this will be negative 1/2 e to the x squared plus c. So that right now you technically found a general solution, right? You have found antiderivatives, there's no derivatives left, so you found a general solution. Usually I said we solve for y, right? So at this point you can choose to find c first and then solve for y, or find y, solve for y and then find c. And here I'm actually going to find c first, so I'm going to do the opposite this time. And the reason why solving for y is very, very difficult on this problem, okay? So we're going to find c first this time around. So we're going to plug in our initial condition. So what are we going to plug in for x? 0, right? That means x is 0, y is 1. So plug in 1 for y. So we'll 1/2 minus ln of 1 is equal to negative 1/2 e to the 0, because x is 0, plus c. What's ln of 1? 0. So this will be 1/2 equals e to the 0 is 1, negative 1/2 plus c. So what's c equal to? Just 1. Yeah. So in this case, it was way easier to find c, right? Pretty easy to find c first. So sometimes you'll just have to choose which way you think you want to do it. So if we plug this back in then for our c, this is going to be our general solution. And we are actually going to leave it like this this is going to be our particular solution. This is our general solution over here. Because we have c over here. So this is our general, this is our particular. But this one is not really possible to solve for y. So there are, on occasion, times where the solution will be left in an interesting form, right? A form where it's not solved for y. But typically, most of the ones you're going to be doing, you will be solving for y. Any questions on this one? Alrighty, I'm going to have you start taking the reins a little bit more on this next one. I want you to kind of try it on your own. I'm going to kind of put the steps up as you go so you can kind of check yourself to make sure you don't get like crazy lost and go down a very bad road. But I want you to kind of try it on your own. So start by separating your variables. Oh, wait, I forgot. This question is secretly a little deceivious. It says, find the equation of the curve that passes through the point 1, 3. And as the slope of y over x squared at any point x. What is this code for? Has a slope of y over x squared at any point xy. That's the derivative, right? Remember, the slope at a point is the derivative. So that means that's code for this is the derivative. And then when it says find the equation that passes through this curve and has that slope, you're asking for the solution, right? That goes through that point. So you're going to find the particular solution. So start by separating your variables. You should have 1 over y is equal to, 1 over y dy is equal to 1 over x squared dx, if you've separated correctly. Then you can go ahead and integrate. When you integrate, you should get ln of y is equal to negative 1 over x plus c. You rewrite this as x to the negative 2. Make sure you have that right, antiderivative. And then you can choose. If you would like to find c first, you can try doing that. I think this is a good one to solve for y first. So I recommend solving for y first on this one. It's going to have a very similar strategy to what we just did on example 3. So try to solve for y first. It's not impossible to do it the other way. But I recommend trying to solve for y first. So try that. So when you solve for y, you're going to raise both to the power of e because you want to get rid of that logarithm, right? So you'll have both to the power of e. This will become y, technically the absolute value of y. And then this is where you're going to rewrite this as e to the negative 1 over x times e to the c. And so you'll have y is equal to some constant times e to the negative 1 over x. Once you have your general form, this is now your general solution because you've solved for y. Go ahead and plug in your x and y values now and find c if you haven't already done that. And I'll say this is probably the most common mistake that I see both in class and grading on the AP test. When you have this plus c up here in the exponent, right, you have to remember it's in the exponent, okay? It can't just drop down here and become a plus c on the outside, right? It becomes times a constant because of this exponent rule, okay? So don't forget to separate that into times e to the c. You should have a times a constant, not a plus a constant, right? But it's really easy for that to just kind of fall down there and just be added on instead of multiplied, okay? So when you plug in your values, you're plugging in 1 and 3. So 3 for y, 1 for x. And so that will be C2 will be 3 over e. And when you plug that back in to find your particular solution, or no, 3 times e, sorry, times e. You'll have 3 times e to the negative 1 over x as your particular solution. But this is actually not usually how you will see the answer written. Yeah.
Could you redo how you got there? I've completely lost you after
So what do you do with this right here?
That's gonna become 1 over e.
And you're trying to find c.
Yeah, and then you multiply that over.
So multiply over there, and now you have this, right?
Yeah.
So we're just plugging back in. 3e
I see.
in there. But this is usually not how the answer will be written. Because would you usually write this as your answer? X squared times x to the 7th, if that's what you got as an answer? What would you write that as? X to the 9th. You would go ahead and add those exponents, right? Do we have two things being multiplied together with the same base? Yeah, we've got a little 1 here, right? So usually you'll see this as 3e to the 1 minus 1 over x. You'll add those exponents together. And this is our particular solution. So once you find C, you're just plugging it back into your general solution. Any questions on this one? Any other questions? Oh, and it does say, be sure to state the domain. There's a particular value that is not allowed to be in the domain here. 0, right? So the domain here will be all real numbers except x cannot be 0. Okay, so last one, I kind of want you to do it on your own as well. The first part A, is just to find the solution. So it's a particular solution because they give you an initial condition. I know it kind of faded on your papers a little bit. That's 3x squared over e to the 2y. It's hard to see. Again, I'll kind of write the steps down for you just to check as you go, but I want you to try it on your own. Separating your variables, you should have e to the 2y times dy is equal to 3x squared times dx. Then you're finding the antiderivatives. Antiderivatives should be 1/2 e to the 2y equals x cubed plus c. This one, it really is not very difficult either way, finding c first or solving for y first. You can kind of pick or choose whichever way you want to go. So if you want to solve for y first, try to solve for y. If you want to find c first, try to find c and then solve for y. Doesn't really make a difference, but do one of them. Try it. Raise your hand if you tried to solve for y first. Anyone tried to solve for y first? Anyone? No? Everyone found c first? Yeah? Okay, well then I'll just do it that way instead. I was going to do it both ways, but I'll just find c first. So finding c first here, plug in 0 for x, 1/2 for y, and you get 1/2 e to the 1 equals c. So c is equal to e over 2. Not too badly, not too shabby. Not too badly, not too shabby. So then we plug it back in. 1/2 e to the 2y equals x cubed plus e over 2. And then we have to solve for y. You're going to use the same strategy whether you solve for y at the beginning or now. First, let's get rid of the 1/2. How am I going to get rid of the 1/2? Multiply. How do I get rid of the e? Yeah, take the ln. Remember, they're opposites of each other. Take the ln of both sides. A lot of our logarithm rules and our exponential rules are coming in. So these will go away, and you'll have 2y is equal to ln of 2x cubed plus e. And then divide by 2. And you get y is equal to 1/2 ln of 2x cubed plus e. If you did it the other way, if you lied and actually did try to solve for y first and then find c, you should end up with the same answer. Sometimes your c's might be different if you have a different constant throughout the problem, right? If you ever get to the point where you try to solve for y and you struggle, then stop, go back, find c first. Usually there's always a differential equation AP problem on the AP test. And you get a point for finding c whether or not you solve for y correctly, right? You get a point for solving for y whether or not you find c correctly. So they're separate points usually. So like if you can't do one, switch over to the other. Yeah.
So that first equation for 1/2 e to the 2y, that's not the particular.
So it is, but we usually want to solve it for y, right? Yeah. Usually they ask us to solve it for y. It's kind of assumed that you want it to be solved for y on the AP test. It did ask for the domain and range. What's the limiting part of this solution? What am I not allowed to have with this solution? Yeah, we can't plug in zeros or negatives into the logarithms. So the domain is going to be restricted by 2x cubed plus e will have to be greater than 0. So if we solve for x here, we'll subtract e, divide by 2. So we'll have x cubed is greater than negative e over 2. So then that means that x has to be greater than the cube root of negative e over 2. So that's the domain. And then the logarithm, right, is going to go all the way from negative infinity to infinity, even though its domain is restricted. So it will just be all real numbers.